Wasabi, y'all! Welcome to Integration Bee Training for Intermediates Part 6. In this video, we're going to be dealing with inverse trig identities. And it's very common in a lot of competitive integration bees. So let's get into this section. So we have this integral here. The identity here, usually it's very nice to memorize this identity. Whenever you have this, this is actually the same value as this as well. Whenever, the inverse is inside. Both of these, they are equal to 1 minus x squared. Okay? It is equal to 1 minus x squared. And I guess the best way to sort of memorize it is if you can imagine yourself, well, if this is theta, if we let theta equal inverse cosine of x, right, then x is equal to cosine theta. And so if you plug that in here, you get 1 minus cosine square, and this equals to sine theta. And that's where you get this sign here. So that's how this goes. And we're going to use this a lot. Now, in this case, we could just turn that integral. This is just 0 to 1, square root of 1 minus x squared dx. And as you can see, this is just an area of a circle. Well, the area of a quarter of a circle. So this would just equal to pi over 4. Okay, so for this integral, we're going to, if you remember, and this is equal to the square root of 1 minus x squared. Okay? So you can actually simplify this, right, in terms of sine, and then in cosine, blah, 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 right? So then, if inverse sine is here, then this is kind of very simple to see. This is just x, and at the bottom, this is square root of 1 minus x squared dx. And this is just straight up just u substitution. So, let u equal 1 minus x squared. You should end up getting something like, let's see, that would be like this. Yeah. This time the inverse is outside. So then you can't really do it. So this is this type of function here is a lot harder to deal with because you can't really simplify it like the one we just did. And the reason is because there is domain restriction going on. Now, thankfully this is an easy integral because at the range of 0 to pi over 2, only at this interval, okay, then inverse sine cosine of x, which is the same thing as inverse cosine of sine of x, they're both equal to pi over 2 minus x. Okay. So this is pi over 2 minus x dx. So now this is pi over 2. Well, I mean, this is technically pi over 2 here. And then minus x squared over 2. I should probably rewrite all this. Let me rewrite all this. So pretty much I just split this integral. This is pi squared over 4. And then minus x squared over 2 from 0 to pi over 2. That's pi squared over 8. So this whole integral would just be pi squared over 8. Oh no. We have a more complicated version, right? We definitely did not go over the inverse tangent and the other complex trig functions. So how do we solve this here? So this is where I probably would rather do the triangle thing, but we're gonna do it quick. We gotta do it quick. So let theta equal inverse tangent. Okay, we're not doing a u substitution. Let me tell you that we are not doing a u substitution. We let theta equal inverse tangent, so that sine theta. So that when we have sine theta, we want to know what this is, right? This is what we're looking for. We're looking for sine theta. Okay, so tangent theta is equal to x, right? Based off of this. Okay, so the way it works is we literally make it equal to x. And when I say x, I mean x over 1. So opposite over adjacent is opposite over adjacent. Oh, by Pythagorean theorem, this is x squared plus 1. Okay, so then what's sine theta? Sine theta is opposite over adjacent. This is equal to x over square root x squared plus 1. Okay, so that's what this is. Okay, that's how we solve it. And so now we have the integral x over x squared plus 1 dx. And this is just square root of x squared plus 1 plus c. Okay. Oh god, this is a lot of inverse trigs. We're definitely not going to have time to do integration by parts, because that'll just take too long. And if you do use integration by parts on this, you will be very sad to how it would turn out. So this is also a very important inverse trig identity that you must know, especially if you want to do like calculus math tournaments. Like, this is something you must know, and that is, for this identity, this is equal to pi over 2. Okay, this will always equal to pi over 2, and same goes for this inverse tangent plus inverse cotangent. This will always equal to pi over 2. Okay, these two identities are very important, and they come up in integration B a lot. Specifically, very competitive ones like Harvard, MIT, Berkeley, Math Soc. This is very very common, and you just have to know these identities if you want to survive their problems. So in this case, this is just, let's see, pi over 2 plus pi over 2. This is just pi, right? This is all it is. That's all it is, right? Can you imagine if you do integration by parts and you just realize, oh, this is all constant, and it's just equals to pi? Oh god, what do we do here? This looks nasty, right? We have inverse tangent of x plus inverse tangent of 1 over x, and they're all being divided by x. So this one is also very tricky to see. It's very tricky to see. But to tell you the truth, this 1 over x is equal to inverse cotangent of x. Okay, inverse tangent of 1 over x is equal to inverse cotangent. So technically, this is just inverse tangent plus inverse cotangent. I just want to throw this at you because this is something you also need to be aware of. And so now this is just pi over 2 1 over x dx. And so this is just pi over 2 ln of x plus c. Alright, now we're going to some legit stuff here now. This, a lot of integration bees will throw this at you because it tricks a lot of beginners. Now, here, this is not equal to x. Be very careful. That inverse is outside. We can't just simplify it as, oh, this is just x. No. No. Okay. Domain restriction. Be very careful. This is an even function. Cosine is an even function. So think of it as an even function x squared. If you do the inverse of it, it doesn't equal to x. Not for all domain, right? It's an absolute value. So this is equal to the absolute value of x. Okay. Because of that, because it's an even function, you can't have negatives, you know. So that's why we have this negative number here that doesn't, you know, there's something going on. So we have to have the absolute value of x, and the absolute value of x is an even function. So if we apply the even symmetry, if you remember, we've multiplied by 2 from 0 to pi, and then it's just 2x dx. Right, this is x squared. So the answer is just pi squared. Okay, it is not equal to 0. You have to be very careful with domain restriction. Oh god, so this looks hectic. Right, this looks very very weird. Oh god, what do we do? This looks very intense. So my first instinct, well, because this is a negative here, can I multiply top and bottom by e to the inverse sine of x? Let's try it. From 0 to 1. Oh, yes, actually, this is good, because you might already see this, right? If we multiply e to the inverse sine, we get e inverse sine here, and then this is plus 1, right? But what about here, right? We're multiplying e to the inverse sine of x, so that's plus inverse sine of x here, and inverse cosine plus inverse sine, that's pi over 2. Awesome! So now this is a u substitution with inverse sine, right? And this is equal to, or I'm going to put a constant here, e to the power of pi over 2, and then inverse of 0, inverse sine of 0 is 0, inverse sine of 1 is just pi over 2. You get du e to the u plus 1. Okay, cool. So then this is just what? We just do algebra here, pretty much. This du, this is technically 1. We just do plus e to the u minus e to the u, right? And now this is e to pi over 2. We could just technically see this very clearly, that this is u minus ln of e to the u plus 1. If you do u substitution, when you split the integral algebra, like we've dealt with this so many times. So now we just plug it in, plug in 0. It's not 0, so be very careful with that. So it's pi over 2. You have pi over 2 minus the ln of e to the pi over 2 plus 1. And then plug in 0, we get minus ln of 2. So it's plus ln of 2. And this would technically be our answer. All this. Okay? I like this integral. So this, again, this is just to terrify people, right? You'll stand there and hesitate. Oh dear God! you know, integration by parts is going to be a pain. But there is a trick. Notice that if I conjugate this, right? Notice if I conjugate this, let me let this be alpha, just a dummy variable, okay? So this, if I conjugate this, right? You know, top and bottom of this, square root of x plus 1 plus square root of x, right? And then multiply top and bottom, you know, conjugation, the typical. So then this is just, well, we know the bottom is going to be square root of x plus 1, square root of x. But then here, let's see, x plus 1 minus x. Oh, shoot. This cancels out. Ah, look at this. 1 over square root of x plus 1 plus square root of x, which is what we have here, reciprocated. So in terms of alpha, we pretty much have, so this is pretty much inverse tangent of 1 over alpha, inverse tangent of alpha, right? No matter what it is, this will always equal to pi over 2, because remember, oh, that's not enough room. If you remember, x inverse tangent plus inverse tangent of 1 over x, this will always equal to pi over 2. Okay? Pi over 2. Because this is the same thing as inverse cotangent. No matter what function this is equal to pi over 2. So, well, I mean, as long as that's not, you know, this can't be 0 for obvious reasons. But, yeah, like this is just a constant. So, very sneaky, right? This is how they can intimidate you. But keep calm. You know, this is just a constant. It's pi over 2. This whole thing is just equal to pi over 2. Okay? Alrighty, so I saved the best integral for last. This is my favorite integral that I've written, and a lot of people, a lot of competitors, what they would do, overly complicated stuff, they would use residue theorem, and I just kind of like oof, like big oof, you know. It's just like it's no bueno. So do not use residue theorem. That's too complicated. That's like complex analysis stuff, and we won't do that. We will not do that. So how would you do this? Right? Well, this is definitely not 0. This is definitely not 0 because this is an even function. So how do we do this? Let me show you a very cool sneaky solution that I come up with. So we know that inverse sine of x plus inverse cosine of x. We know this identity is equal to pi over 2. So let me go ahead and do this. Pi over 2 minus inverse sine of x. Ah, this is my sneaky solution that no one suspected. Right? You don't need residue theorem. You don't need to do something complicated like what? Frickin' Laplace or whatever. Feynman technique or something like this is. No. Just do this. Right? It's just pi over 2 minus inverse sine of x. Now watch this. Now, inverse sine of x. Inverse sine of x. This is just an odd function. That's an odd function. So when you split it, this whole thing is just equal to pi over 2 over x squared plus 1 dx. Mind blown, right? So this is just inverse tangent, straight up, pi over 2. I mean, this is an even function, so you could just sort of multiply it by 2. Inverse tangent of x from 0 to 1, right? Symmetry, even symmetry. And so now this is just what? What's inverse tangent of 1? Pi over 4, right? So this is pi over 2, pi over 4 times 2, that's pi over 2. So the answer is pi square over 4. You see how simple that was? No residue theorem, no anything nasty. This is just pi square over 4, just based on an inverse trig identity. Okay. A very cool solution. Something that something you won't be able to unsee. All right. So that's all of the. Oh Jesus Christ! So that's all of the integrals I have for this lesson. I hope it's very helpful. This does come a lot in very competitive integration bees, so it's very good to be aware of these techniques and identities. All right, so I hope that helps. Thank you guys so much for watching, and I'll see you guys in the next video.